Welcome back. We have up to now discussed the design considerations and the manufacturing process of crystalline silicon solar cells. In this video, we will shortly introduce the technical considerations for manufacturing solar modules from wafer-based crystalline silicon cells. The learning objectives of this video lecture are to understand the principle of how solar cells are or can be interconnected in photovoltaic modules. What is the impact of shading over the module, and what is the role of bypass diodes? How and what materials are used for the encapsulation of cells in the final module product? A wafer-based device is usually referred to as solar cell. A solar module is a larger device in which many solar cells are connected. If you look at the level of a photovoltaic system, we can have several modules connected, and this is what we call an array. The dimensions of the solar cells in the industry have been increasing rapidly during the last years due to advancements in the ingot manufacturing. A few years ago, 6" by 6" or 15.5 by 15.5 centimeters were the common wafer sizes used. Currently, wafers of 21 by 21 centimeters are becoming the mainstream size. A solar module consists of many solar cells interconnected in a circuit. As of today, the most frequently used design has 60 to 72 individual cells with total dimensions of 1 meter by 1 meter 65 up to 2 meters. In photovoltaic systems, these modules will again be interconnected to form an array. In order to connect individual solar cells in a module, the bus bars at the front side will be connected to the back contact of the neighboring cells. This process is called contact tapping. Here you see a cross-sectional view of a few solar cells connected in series. Such a series connection is called a string. There are other ways to interconnect solar cells, such as the earlier discussed metal wrap-through technology. Here, the front contacts are wrapped through the cell with a so-called via, such that both the positive and negative terminals are located at the backside of the cell. The cells can now be placed much closer to each other since contact tapping is omitted. A more advanced way to place all the contacts at the backside of the solar cell is found in the earlier discussed interdigitated back contacted technology. Both the electrons and the holes will be collected at the backside of the cell by alternately placing a P plus and an M plus layers that serve as the selective contacts. In this slide you see a cross-sectional view of a few solar cells connected in series. Every solar cell has its back contact connected with the front contact of its neighboring cell. For series connected cells, the voltages will add up, whereas the current does not add up. The current flowing through the solar cell is determined by the photocurrent in each solar cell. It means that the total current in the string of the solar cell is equal to the current generated by one single solar cell, or the cell generated the lowest current. Let's look at the IV curve of solar cells connected in series. Here you see the IV curve of a single solar cell. If we connect two solar cells in series, it means that we can add up the voltages. However, the current, as mentioned earlier, remains the same in series connection. The resulting open circuit voltage is 2 times that of the single cell. If we connect 3 cells in series, the open circuit voltage becomes 3 times as large, whereas the current is that of one single solar cell. A second way of connecting the solar cell is in parallel. Parallel connections means that the voltage is the same over all the solar cells, however, the currents of the solar cells add up. If we have two solar cells connected in parallel, the current increases 2 times, whereas the voltages remains the same. If we have 3 cells in parallel, the current becomes 3 times as large, while the voltage is the same as for a single cell. This means that if we consider a module, you can partly tune the voltage and the current output by the arrangements of the connections of the solar cells. Now we look at how we make a solar module out of an ensemble of solar cells. Here we see a solar panel that contains 36 solar cells connected in series. If a single junction solar cell would have a short circuit current of 80.5 amps and an open circuit voltage of 0.6 volt, it means that the current output of the module is equal to that of a single solar cell, which is 8.5 amperes. The open circuit voltage would be 36 times that of a single junction solar cell, which equals to 21.6 volt. If we would rearrange the interconnection of this module, we can get a different current and voltage output. If we connect 2 strings of 18 series connected solar cells in parallel, we would get a short circuit current of 2 times that of a single solar cell, which is 17 amperes. The open circuit voltage would be 18 times that of a single solar cell, which is 10.8 volts. Another aspect of modules is that some bypass diodes are integrated into the modules. Why do we need bypass diodes? For that we have to look at a solar module in real life. In real life, the solar module can be partly shaded. This can be the shade of an object nearby, like a tree, a chimney, or a neighboring building. The shading can also be caused by a simple leaf that has fallen from the tree. This can have significant consequences for the output of the solar module. Let's consider the situation in which one solar cell in the module is for a large part shaded. For simplicity, we assume that all 6 cells, part of this module, are connected in series. This means that the current generated in the shaded cell is significantly reduced. In a series connection, the current is limited by the cell producing the lowest current. This cell dictates the maximum current flowing through the module. In this IV curve, we show the theoretical IV curve of 5 non-shaded solar cells and 1 shaded solar cell. If we have a constant load, like a resistance R in the previous picture, it means that the voltage over the module is dropping due to the lower current generated. However, since the 5 non-shaded solar cells are forced to produce high voltages, they act like a reverse bias source on the shaded cell. The dashed line represents the reverse bias load put on the shaded cell. It is the IV curve of the 5 cells mirrored into the vertical axis equal to 0 volts. This means that the shaded solar cell does not generate energy, but starts to dissipate energy. It means the solar cell is getting warmer and warmer. The temperature can increase to such critical level that the encapsulation material cracks or other materials wear out. This can be prevented by including bypass diodes in the module. In this figure, you can see bypass diodes included in the electric circuit. A diode, as discussed in part 1 of this solar MOOC, blocks the current in the direction when it's under negative voltage, but conducts a current when it's under a positive voltage. If no cell is shaded, no current is flowing through the bypass diodes. In the case that one cell is shaded due to the biasing of the other solar cells, the bypass diode starts to pass the current through. As a result, the current can go around the shaded cell and the module can still produce the current equal to that of a non-shaded single solar cell. Before we conclude this video, we will show the basic structure of a crystalline silicon solar module. On the backside of the module, a junction box is placed that encloses the string interconnects and brings out a positive and negative terminal cable that can be connected to an inverter or to other solar modules to form an array. The junction box is located underneath a plastic or a glass backsheet. The solar cell itself are laminated between two layers of encapsulation foil to prevent air and moisture ingress. The most common encapsulation materials is ethylene vinyl acetate or EVA. The front surface of the module is protected with a sheet of tempered glass to make the module impact resistant. Finally, the sides are first sealed and then protected with an aluminum frame such that the module can be mounted on support structures. As you can see, going from a solar cell up to a module gives rise to a whole new set of technical considerations. In part 3 of this MOOC, we will discuss the operation of modules and design considerations in the PV system in greater detail. In summary, solar cells are placed in series and in parallel to form photovoltaic modules. Cell overheating by shading can be avoided with bypass diodes, and encapsulation is important to make PV modules weather and impact resistance. So this week, we have discussed crystalline silicon wafer-based PV technology. I hope it was a helpful introduction into this technology. You have to realize that in view of the time limits, we only covered the most rudimentary concepts. In the next week, we will discuss different PV technologies which are based on thin film materials, such like amorphous and nanocrystalline silicon, cadmium telluride, CIGS, 3,5 semiconductor materials like gallium arsenide, organic materials, and perovskite materials. Recently, the new kid on the block. You will discover that every technology will have its own specific design rules and challenges. So, looking forward to see you in the next videos.